Welcome back to another explainer. Look, if you're a focused learner trying to demystify system design at a massive scale, you are absolutely in the right place. Today, we're going to build a mental map of how engineers actually estimate resources for a giant, Twitter-like service. We are talking hundreds of millions of users, massive data centers, and back-of-the-envelope calculations, or BOTs, that literally dictate whether a multi-million-dollar project lives or dies. We're going to quantify server counts, figure out true storage needs, and calculate network bandwidth totally from scratch.
Okay, let's dive right into this. Here is our step-by-step roadmap. First, estimating servers. Second, managing peak load. Third, calculating costs. Fourth, storage needs. And finally, bandwidth requirements.
All right, Section 1, estimating servers and establishing our baseline assumptions.
Here is the sheer raw scale we're dealing with. We're assuming 500 million daily active users, or DAU. Next, we estimate an average of 20 requests per user per day. And finally, we need a baseline for our hardware, right? We're assuming a single server packing 64 cores has a capacity of 64,000 requests per second, or RPS.
Okay, let's run the math on those assumptions real quick. 500 million users multiplied by 20 requests gives us a staggering 10 billion total requests per day. To find our per second load, we just divide that 10 billion by the 86,400 seconds in a day, which lands us at roughly 115,000 requests per second. Since one server handles 64,000 RPS, dividing 115,000 by 64,000 gives us our answer. A grand total of just 2 servers? Let's figure out why that feels suspiciously low.
Wait a minute. 2 servers? To run a global service for 500 million daily active users? Absolutely no way. You always have to judge if numbers are reasonable, and this plausibility test screams that something is terribly wrong. Can you spot the hidden assumption in our calculation? The flaw here is that we assume traffic is perfectly, evenly distributed across every single second of a 24-hour day. And well, in the real world, that literally never happens.
Moving on to Section 2. Managing peak load and handling flash crowds. So, to estimate true peak capacity without relying on super complex statistical models, we use a simpler proxy. We just treat our total daily active users as the number of requests per second. Yep, we're going to assume all 10 billion daily requests arrive at the exact same time. So, 10 billion divided by 64,000 RPS jumps our requirement from 2 servers to 157,000 servers.
Talk about whiplash. We've swung from an impossible 2 servers to a completely unfeasible 157,000 servers. To address this massive discrepancy, engineers generally have 2 options to fix the architecture. Solution 1, we drastically improve the performance of our single servers. Or, Solution 2, we fix the extreme math of our peak load assumption. Let's look at option 1 first.
If we're physically capped at, say, 100,000 servers, we would need each server to handle 100,000 requests per second to hit that 10 billion mark. Increasing RPS from 64,000 to 100,000 requires some seriously heavy engineering optimization. But, it is possible with immense R&D. For example, back in 2012, WhatsApp managed an incredible 2 million concurrent TCP network connections per server, allowing them to run their massive service on just about 700 servers by 2017. Or think about a recent I/O research system that sorted 1 trillion records in just 172 minutes, using only 25% of the resources of the previous record holder. That represents a massive 3x improvement in RPS.
Now, if you don't want to rely purely on extreme hardware optimization, we look at option 2, which is improving our load assumption using the Pareto principle, also known as the 80-20 rule. Instead of assuming all traffic hits instantly or perfectly evenly, we assume that 80% of our daily traffic occurs within 20% of our time. 20% of a 24-hour day is exactly a 4.8-hour window. This concentration actually reflects real human behavior. People generally check their phones during morning commutes or lunch breaks, right?
Let's see how this builds a much more realistic picture. We take 80% of our 10 billion requests, so that's 8 billion requests. We divide that by our 4.8-hour window converted to seconds. That gives us a realistic peak load. Divide that new load by our server capacity of 64,000 RPS, and the result? Approximately 8 servers. Just 8. By applying the Pareto principle, we literally brought a terrifying 157,000 server estimate down to a highly realistic, manageable 8 servers. Just remember, systems built on these assumptions require strict monitoring.
If the load exceeds predictions, we have to employ techniques like load shedding and circuit breakers so our limits aren't violated.
Section 3. Calculating costs, specifically our server costs. Now, what's really interesting here is we can pin down exact numbers for this. For our 64-core server, we are modeling against an AWS EC2 M7i.16x large instance. It features 64 vCPUs, 256 GB of RAM, a 4th-gen Intel Xeon processor, and a network bandwidth of 25 gigabits per second. If we lock into a one-year contract, this exact beast of a machine costs exactly $3.54 8/16 per hour.
Let's look at how our previous assumptions impact the budget. Our naive estimate of 2 servers would cost us just over $7 an hour. Our highly optimized Pareto calculated setup of 8 servers costs a very manageable $28.38 an hour. But our unoptimized peak load scenario, running 157,000 of these servers would burn through $557,061 every single hour. You can totally see why getting the math right isn't just about the code, it's about the financial survival of the entire company.
Section 4. Storage needs and estimating our footprint.
To calculate storage, we start with a fresh set of assumptions based on our 500 million daily users. Let's assume each user posts 3 tweets per day, giving us 1,500 million, or 1.5 billion, daily tweets. Next, the media breakdown. We're going to assume 10% of tweets contain an image averaging 200 kilobytes, and 5% contain a video averaging 3 megabytes, mutually exclusive of each other. The remaining tweet text and metadata average roughly 250 bytes.
Let's methodically walk through the daily storage math. First up, the text. 1.5 billion tweets at 250 bytes each equals 375 gigabytes. Honestly, not too bad. Next, images. 10% of 1.5 billion is 150 million images at 200 kilobytes each, yielding 30 terabytes. Finally, the heavy hitter, video. 5% of 1.5 billion is 75 million videos at 3 megabytes each, resulting in a whopping 225 terabytes. Adding 375 gigabytes plus 30 terabytes plus 225 terabytes gives us a daily storage requirement of roughly 255 terabytes. Notice how video utterly dominates the footprint here. And here is where the scale truly sets in. That 255 terabytes is just for a single day. To find our annual storage needs, we multiply 255 terabytes by 365 days. The result? 93.08 petabytes of new storage required every single year. To put that into perspective, that's enough to store something like 20 million high-definition movies. It is a colossal number, for sure, but entirely plausible for a platform hosting hundreds of millions of media-sharing users.
Section 5. Calculating bandwidth requirements and defining our network limits.
To translate all those massive storage sizes into actual network speed, we use a simple 3-step formula. First, we estimate the daily incoming data, so the uploads. Second, we estimate the daily outgoing data, the downloads and views. Third, we just divide those daily totals by the number of seconds in a day to determine our required speed in gigabits per second, or GBps.
So the absolutely crucial point for incoming traffic is tying it right back to our storage calculation. We know users upload 255 terabytes of data daily. To convert that to gigabits per second, we multiply 255 terabytes by 10 to the power of 12 to get bytes, and then multiply by 8 to convert bytes into bits. We divide that massive number by 86,400, the seconds in a day. The formula lands us at roughly 24 gigabits per second of incoming traffic.
Now, outgoing traffic is significantly higher, simply because a single tweet is viewed many, many times. We'll assume each of our 500 million users views 50 tweets per day. That is 289,000 tweet views every single second. Applying our media ratios, where 50 tweets contain 5 images and 2.5 videos on average, we crunch the numbers. The text bandwidth requires 0.58 Gbps. Images demand 46.24 Gbps, and viewing videos consumes a staggering 346.8 Gbps. Add all those up, and our total outgoing bandwidth requirement is 393.62 gigabits per second. Let's combine them to see our final network architecture constraint. Assuming uncompressed uploads, we take our 24 gigbits incoming traffic and add it to our 393.62 gigbits outgoing traffic. This gives us a massive total bandwidth requirement of 417.62 gigabits per second. Remember, these calculations heavily depend on your specific traffic mix, the ratio of text to media, and the ratio of reads to writes. So, we've designed a system for normal operations using the 80-20 rule. We mapped out its 93 petabytes of storage, and we provisioned 417 gigabits of bandwidth. But I want to leave you with a final, slightly provocative thought. Consider a massive global news event, like 9/11, where flash crowds suddenly flood your service for updates. Suddenly, all your daily users arrive simultaneously. Your load assumptions break entirely. Ask yourself, as the architect, how will you implement load shedding and throttling to ensure this massive system degrades gracefully rather than crashing completely? Understanding the math is really only step 1. Surviving the real world is step 2. Keep learning, and I'll catch you on the next explainer.